Hello, everybody. Welcome back. In this lesson, we will go over the significance or the meaning of the derivative. The derivative is a mathematical concept that has a wide variety of applications. To understand these applications, we need to understand what it means in the context of geometric interpretation as well as the physical meaning. When you consider the geometric meaning, it can open up many geometric properties that you can employ in applications. And when you consider the physical interpretation of the derivative, you can consider variety of applications in real world setting. So now to understand, first of all, the meaning of the derivative, as we mentioned here, you can see uh, there are two directions. Geometric. The geometric meaning is none other than the slope of a graph. So what do we mean by the slope of a graph? So we consider the slope of the graph at a given slope of the tangent line to a graph at a given point. So what do we mean by that? You will see that in graphical sense in a moment. But on the other hand, when you consider the physical significance, physical meaning of the derivative, that is the rate of change. Of course, we can consider the rate of change in different contexts, but this is not going to be an average rate of change. Instead, we consider instantaneous rate of change. What do we mean by that? You will see that in a moment. So first of all, let's get started with the geometric interpretation, the geometric meaning. The geometric meaning, which I mentioned already, it is going to be the slope of the graph. And to explore this possibility, to explore this connection, first of all, recall the definition of the derivative. The definition itself is right here. We have seen this. This is the limiting process for the derivative computation in one way. On the other hand, this is exactly the connection that this is exactly the formulation that we are going to employ to see the geometric meaning. On the other hand, the other component is something fairly straightforward. When you consider any straight line connecting two points, x1, y1, and x2, y2, the slope of that particular point, that particular line is given by y2 minus y1 divided by x2 minus x1. It should be x1 here. Let me update it. x2 minus x1. So as a quick recap, if you consider x1, y1, and another point x2, y2, and if you combine these, if you connect these two by a straight line segment, and if you ask the question, what is the slope of this straight line? You know how to compute it. It is just the slope formula, y2 minus y1 divided by x2 minus x1. And this is going to be important in our computation. So both of these ideas, these pieces will be connected together to see the geometric meaning of the derivative. So let's get to that point. Now, let me do this first. Let's first draw a graph of a function, any arbitrary function. So I would just make it look like this for convenience. This is the graph that I'm looking at, y equals f of x. And we know this is the x-axis, we know this is the origin, we know this is the y-axis. We've labeled them. And then we know there is a significance. Now let me rewrite this here. I'm trying to connect the interpretation of this formula. I'm trying to look at this formula and see what this means. This is the meaning of the derivative, right? I mean, this is exactly the definition of the derivative. So let's try to prepare this one here. To prepare that, the first thing that I need is, now there's a constant here. Can you see x goes to a, and here fa, here x minus a. There is a significant point, and at the same time right here, at this point, you can see the derivative at point A. So I will indicate point A right here. This is my point A, which is going to be a fixed number, fixed point. It is already fixed. There is no variability in that. And then in the next step, what I'm going to do is to figure out or to write the corresponding point on the graph, right? So on top of, just right on top of A, you have this point. Now, if you look at carefully, this point corresponds to a height on the graph, but don't forget we're dealing with function f at f of x. So this particular height that you're considering is none other than the y coordinate f of a. The height is always measured by the function. That is a connection between x and y when you consider a graph. Now, this simply tells us a very simple story. When you look at this point, now, not to overwhelm our picture here, I will erase what I'm writing here in a moment, but for now, just try to visualize this. The x coordinate at this point is none other than A, and then the y coordinate of the same point is f at A. Now, we have one point in this on this graph where we know both the x coordinate and the y coordinate. Now, let's go back to this formula. We have everything related with A in this case, right? F at A, and x goes to A. And on the other side of this story, we have x, f of x, and x is going towards A. So now to understand the nature of A, to understand the nature of x, let me move this one right here so that I'm not. Let me do this. Let's get rid of this for a moment because it's on the way. Let's delete it. Whenever we need it, we can write it back. So the next point that we're going to look at it is going to be the variable x. I'm going to place variable x somewhere on a different location. X. And the significance of this quantity is this is a variable. That's a variable. And on top of that variable domain value, I can prepare the corresponding point on the graph. And that corresponds to f of x, because you have the x coordinate just as plain x, the corresponding y coordinate, generic as a generic computation, it is going to be f of x. Now, we do have these 2 points. Now, since we have all of these points, needed points, why don't I go ahead with this coordinates one more time? Here, right here, I have A, F, A. That's the coordinate of this. And then this point corresponds to X, F of X in the similar way. Now, you may be able to see the connection between the point slope formula that we had a few minutes ago. Now you have 2 points on this picture. And in this picture, when we have 2 points, what we're trying to do is to connect these 2 points. Now, let me do this. Once we have 2 points, why don't we go ahead and connect them by a straight line? I have to be very careful when I navigate these pictures. All right, so here we have 1 point right at the beginning, the red point, and then we have the green point, and there is a straight line through those 2 points. And this kind of a line is having a specific name. We call it a secant line. What is the meaning of a secant line? A secant line is a line connecting 2 points on a graph. 2 distinct points on a graph. That's exactly what we can see here, right? We do have two distinct points and we connected them by a straight line, and here we have a secant line. Now, if I ask you to write down the slope of the secant line, one can do it blindfolded, right? So look at this. The slope of the secant line. Slope of the secant line. Let me manage the space better, moving this onto the left corner and writing down an equality. Now, the slope of the secant line is none other than from the point slope formula, y2 minus y1 divided by x2 minus x1. So this is like y2, this is y1, this is x2, and this is x1. So let's write it. F of x minus f at a divided by x minus a. By any chance, if you do not see this connection, pause the video for a moment, write down the point slope formula for one more time, and make sure that you understand, you see that connection properly. Now, once you have this, once you got this idea, now, can you see this was the key component in the definition that we wrote down a few minutes ago? So what we need to do is, in the next step, is to move this point, variable point x, towards a, so that you can have this limiting process. So this limiting process will result something. Now, to understand that, let me have another point here. Let's say what I started moving point x towards the left side because I need to catch a somehow. So I started moving to the left according to this picture. So when I do that, now let's say my new location of x is right here. If that is the case, on top of that, I do have that function value right there, given by the blue point right here. Now let me just do this. Let me employ a different green color, not the same. And this is a fixed point already. And through that, I'm going to catch the next point. Now, this is the observation. This is also the next, another secant line. But now look at this. Can you see very nice observation here? The first secant line is actually, it is vibrant. You can see actually it is a secant line. But the second one seems almost like tangent. It is just like touching the graph, and apparently it is not, like you do not see even that line is cutting the graph at two different points because of our drawing, the limitations of our drawing. But when you reconsider, you can clearly see there are 2 points. We have the red point and the blue point, and we combine them by using this light green line, and we end up getting this second secant line. But now, if you keep moving in this way, if you keep up with this process, let's move this point x further. If I do that, I'm going to end up getting even closer approximation to this tangent. Now, can you guess what would happen eventually when we get to the point where x is actually coinciding with a? We are not going to coincide x with a technically, but what we are going to say is like the eventual outcome of this limiting process. So that would result us not 2 points. Instead of having 2 points, we will get exactly 1 point right here. That is a red point. And at red point, you have a line, which I did by, what is this color? Is it gold color or is it brown? We can call it brown, right? So this brown line has a significance. That is called a tangent line. that is the tangent line at x equals a. The significance or the difference between the tangent line and the secant line is the secant line is intersecting the graph at two different points, but the tangent line is touching the graph only at one single point. It is touching the graph, but it is not abruptly intersect the graph in two different points. So now, of course, like when you extend the graph, it can intersect the graph in a different place, but we are looking at this local behavior, right? Locally around point A, what happens is it's just touching the graph. It is tangent to the graph. So now the calculus, the whole beautiful story of calculus is just summarized at this point. When you try to compute the slope of the tangent line, you do not have 2 points on your hand. But the only way that you know how to compute the slope is to employ 2 points. That's exactly by using 2 points and the secant line. So what we do is to have the slope of the secant line, and when we consider the limit of x when x tends to a, or when the variable point tends to that fixed point, we will end up getting exactly the slope of the tangent line. So the simple idea is, now when we unwrap this, we can see f prime a, this is none other than the slope of the tangent line at x equals a. And that is none other than, it is going through this nice process, right? To get to that, first of all, that's a question. That's the big question that we ask in calculus right at the beginning. If you read the history of calculus, this started in the 16th and 17th centuries, this particular conversation, where we need to have rate of change, or especially the dynamics of objects. How can you define the speed and the velocity and acceleration? How do you start? That's exactly the starting point where you need to have instantaneous consideration rather than considering like average motion of an object. So that's exactly what we are doing here. Now in this case, first we look at the average consideration. This is the average, or the slope of the secant line on an average. It is an average on an interval x and x to a. And then we consider the limit from x going to a, and this limiting process concludes our slope of the tangent line, right? So to have some placeholders here for your information, this is exactly the slope of the secant, variable secant line. And then the golden property here, the golden information is right included here. This is the process. The limit process is the magical process that converts the secant line to a tangent. So this is what you need to understand regarding the geometric meaning of the derivative. So the geometric meaning of the derivative is none other than the slope of the graph given by that quantity given by the function. So slope of the graph can be visualized in a different way, slope of the tangent line at that given point. So slope of the graph is exactly same as the slope of the tangent line. All right, so that's exactly what you need to understand here. So this particular conversation is a qualitative conversation, so I do not have any computations behind this. Already we have seen the computations behind derivative, the definition of the derivative. And now let's proceed to the physical meaning of the derivative. And this is a byproduct of what we have seen already, but I will be more descriptive. Now, the physical meaning of the derivative, first of all, what does it mean? It means a rate of change. That is what, at least that is what the um, literature would say. It will call it the rate of change, but precisely it is going to measure the rate of increase of a certain quantity. So when you consider a function, now in real world, functions are, when you walk around, you will not see functions just like function f of x, function g of x, the graphs. You do not see them floating around in the real world. But what you see is dynamical processes. You will see dynamical processes, you will see applications, you will see cost of a certain business. Cost is a time variant quantity and it is a function. And the profit of a business, it's going to be something time varying, it's a variable, it's a function. And when you consider the dynamics of, like, let's say celestial objects, like the planets, comets, that means this dynamics. So we can derive, when wherever we have dynamics of certain components, certain quantities, we can derive the concept of rate of change behind it. But now, when you consider rate of change or rate of increase more precisely, how can it be connected to this concept of the derivative? Now, the idea is pretty simple. First of all, uh, imagine imagine a dynamical process. Something that I can come up with is like, very simple example, the motion of an object on a straight line path, like, so that I can make it super simple. So there's an object and it's moving to the right, let's say for convenience. And at time t, when you start measuring time, you can see like it's right at this point, and then it starts moving, and then at time t you observe it somewhere here. Now if I ask you the velocity, or like, let me make it more simple, let me call it the speed. If I ask you to compute the speed, one can say like, oh, that is just the distance. You know the time duration from here to there. The time duration is going to be just t, let's say seconds or minutes, and then d divided by d is the distance divided by the time. That should be the speed. But now when you do this, you forget an important, very important scenario behind this. Or you assume, you make a huge assumption to have this equation. What is that assumption? You assume that this motion is linear. In other words, it is just a constant speed. So the real question is it, can it be constant speed? Let me show you. Now I will have that constant speed with that question mark, because that's a big question mark. Now, to explore it a little more, let me show you. Now, by any chance, if the speed is constant, this is how it would look. This is the position, or in other words, the distance, simply in simple words, and the time. And if this object is moving at a constant speed, like let's say 20 miles per hour, or 20 meters per second, you have it. So as far as it's constant, you will see the increase of the distance constantly, right? So it will be a straight line. Now in this case, if you do this, it makes sense, right? 0 and then time t, and then if you consider the scenario, right, after time t, you can see the position or the distance to be just d. Now if you try to make the uh, formula for the speed or the rate of change of position in this occasion, It's going to be, of course, I will just name it like V. So speed or the velocity is indicated by V. It is none other than d over t. However, this is not the realistic scenario. This need not to be the realistic scenario. To see that, let me just have another picture where we are going to have, let's have time and position, yet the same thing. In other words, the distance. And then other than having a linear motion, let's say this object is undergoing an acceleration. It starts slow and then it starts picking up its speed due to a certain force. And it's going to increase its speed gradually like that. If this is the case, now if I ask you, okay, tell me what's the speed of this? It starts at 0, and then at time t, of course, you're going to observe uh, the distance d. Now, if I ask you the speed of this object, now this is not exactly the same slope, the same incline that you're going to see, because if you do that computation, what you're doing is essentially you're measuring the slope of the straight line connecting these 2 points, the starting point and the end point. But can you see, since this velocity is increasing, this has a different story to tell us. If you really try to measure this speed of this object, you need to measure how fast it's increasing at that point, that particular point. In other words, this is the tangent line at which point? At that point. So since that is the tangent line given at this point, now we do not have 2 points here. We need to consider one single point to come up with the velocity. The important idea about this speed or this velocity is this is this gives you an average velocity. In fact, like in this scenario, it coincides with exactly the instantaneous velocity because it is already a straight line. However, in this scenario, this tangent line, the slope of this tangent line is going to give us the instantaneous velocity or the speed at that particular moment. And that is the key component behind this. To talk about dynamics of real world objects, we cannot have just average. Now think about, if you do not see the significance or the difference between these two, this is my recommendation. Let's employ a different color and let's draw the other version of it. If we get the average speed in this occasion, average speed is given by just the straight line segment connecting these 2 points. And look at the slope of this yellow line. Compare it with the slope of this pink line. Can you see the difference? And that difference is going to matter in applications, because when you precisely trying to when you try to model dynamics of dynamical processes precisely, you need to know what the rate of change is precisely, and that is what's given by the derivative. So this important concept, the way that it's going to work, now we are going to see that in upcoming sections, but right at the beginning, we need to have this particular idea to get motivated and to see what's really happening. Now, as a summary, this is what I can say. The derivative it has millions of applications, and all of these applications are motivated by two different directions. One direction is the slope, which is the geometric idea, and the other one is the rate of change or rate of increase. In fact, any component, we will see that more in detail later. And when you consider the slope, you will have graphing, graphing of functions or visualization, or sometimes even optimization, some important application, geometric applications. And then when you consider the rate of change, you're going to see only the real world applications, like let's say maximum, or like uh, let's say rate of change of change of a price in of an object, of a certain commodity in the market, right? In the stock market, if you consider, right? So when you consider some commodities, some specific objects, like let's say rate of change, you need to keep eye on this, right? You need to make quick decisions sometimes. Rate of change of this, and then let's say some physical applications where you have velocity, um, acceleration, and then all sort of physical plus all physical and real world scenario. Let me emphasize this word: real world applications. Real world applications are coming from this branch. So the takeaway of this particular qualitative conversation, now here we did not have any computations. Don't worry, you will see them soon. But at this point, I wanted to emphasize the qualitative idea. What are we dealing with? Either geometric significance or real world significance in terms of rate of change. So that's the meaning of the derivative. So we will see this more in detail in upcoming lessons, especially with applications of the derivative. But in the next lesson, we are planning to see the computations. All right. So with that, we are going to conclude this session. Let's meet on the next one, next session on applications on computations of derivatives.